let's just go over some of the basic vector ideas you guys have been working with. You guys have been doing a bunch of stuff with vectors, drawing them, the whole component thing, adding, subtracting, multiplying, dividing. Let's just go over some of the basics we've been looking at in terms of vectors and how they work, and apply them to maybe some simple situations and stuff like that. So here's got 4 scenarios. We're looking for the net resultant force vector in each of these situations, basically just putting vectors together. So you have the first guy there, we got a guy, pushing wheelbarrow. If he's pushing forward with 50 and friction would be 5 newtons back, it's basically a vector going to the right, putting it together with a vector going to the left. Obviously, it would be 45 newtons to the right. That would be the net force vector, just putting those 2 vectors together. Here we got a rocket ship. You've got 1,480 newtons going up, which is pretty pathetic for a rocket ship. And the weight holding it down would be 480. So you got 1480 going up, you got 480 going down. That would leave you with only 1,000 newtons going up. So that would be those 2 put together. Here we've got a car, 200 pushing it to the left. Friction is 20 going to the right. So we put the 2 together and we'd end up with 180 newtons to the left. You could also put it, negative 180. I like to use arrows when I can. I just find a lot easier. And the last one here, 400 or 540 newton weight, flotation of only 20 newtons. By the way, that means they would actually be sinking because that's just the way buoyancy works. But anyway, it doesn't matter. You'd subtract the 2 going in opposite directions. The net force would be 520 newtons going down. So just putting simple things together. All right, so let's look at another aspect of vectors you guys have worked with. And that would be component type stuff, working with components. So finding the components of these vectors, okay? All right, no problem. Now, the first 2 here, we've just got giant arrows drawn here. And we don't really have any other information about them, so we'll actually have to measure them to figure it out. And I'm just going to draw. What I would do is I would start a little nub here, and I would just draw sideways. That's my x component, and then down, something like this. And I'm just literally going to have to measure it. Now, of course, I'm measuring on a computer screen, and measuring it on paper or a computer screen could be totally different. Like for me, this vector is around 3 centimeters long, so I'm not sure how long it is on your paper or something like that. Hopefully something close to that. But when I measure the x component on my computer, it's around 2.7, and my vertical part here is around 1.8. So my x component would be negative 2.7. It's negative because it's going to the left. And my y component would be negative 1.8 because it's going 1.8 down. All right, similar for the next one. I'm just going to turn it into a right triangle, a little bit low, something like that. All right, and again, on my computer screen, let's see, I'm measuring it. It looks like around 3.3, so I don't know if it's close for you. If I look at the sideways part, I'm just measuring it with a ruler. It's going to the side around 2.6, and the vertical part is around 2, I guess, somewhere around there. All right, so my x component, got the 2.6. It is going to the left, so I'd make it negative 2.6. And my y component would be 2.0, and it's going up, so it can stay positive. All right, so next one we have got actual numbers, so we can actually calculate stuff with them, which makes things a little bit easier, a little more accurate, but I still want to sketch it anyway. So we got 46 at negative 55. So if I make a little reference axis, of course 0 degrees is straight to the right, so negative 55 would drop down. So that'd be like 55 degrees like that, swinging down. So I would do 46 cos 55 and 46 sine 55. So if I do 46 cos 55, it will give me a value of about 26.4. And it's positive because it's going to the right, so no problem there. If I do the 46 sine 55, I will get a vertical component of 37.7. And since it's going down, I'll make it negative 37.7. So something like that. Okay, next one, we got the 0.85 at 160. So again, I'm just going to sketch that out a little bit. So we'll reference 160 degrees is out this way. So that's the 160 wrapped around. I would use the little 20 degrees in there. That's what I would use. So I'm going to do 0.85 cos 20 degrees. And you can use the 160 if you want to. It doesn't matter too much. And I'll get an x component of 0. Well, round off 80. And it is going to the left, so it will be negative. And my y component, so I'll do the 0.85 sine of 20 degrees. And I will get a y component of 0.29, and it is going up, so I can just leave it the way it is. Okay, next one. 75 is southeast. All right, going southeast. Okay, let me start my little reference again. South, of course, is down. East is to the right. And it's perfectly southeast. So it's right at the 45. Let's actually get the line tool, arrow tool. It'd be right at the 45, something like this is what it would be. The nice thing is, since it's right at the 45, I know that my x and y components are going to be the same. So when I find my x component, it's going to be the same for my y component. So if I do the 75 cos of 45, I've got a component of 53.0, and this one's also going to be 53.0. It's going to the right, so my x component's positive, but it's going down, so my y component would be negative. All right, and then this last one here, again, I'm going to draw a little reference. Make things easier for myself. All right, so I am going 480, 25 west of north. Okay, so I'm going west of north. So I'm going to start with north. So that going straight up would be north, and then I'm going to go 25 degrees west of it. Something like that. I'll move that over a little bit. That's a little better. Okay, so this should be the 25 degrees right there. That's 25 degrees west of north. I wouldn't really want to use the 25. I like to use my angles from the x-axis, so I would instead use the 65. So I'm going to do 480 cos 65 and 480 sine 65. So if I do 480 cos of 65, I get around 203. And if I do 480 sine of 65, I get a y component of 435. It is going to the left, so my x component should be negative, and it is going up, so my 435 is fine from the y component. Okay, so this is just more practice finding x and y components and that type of stuff. And for the E and F with the compass directions, some people would do, x component is 53 east, y component is 53 south. Some people, for the last one there, would do the x component is 203 west, and the y component is 435 north. I just use the positive negatives once I've got the description out of the way. I just find that a lot easier. Okay, all right, so let's do some more questions with this type of stuff, except actually applying it possibly to sort of like some little situations and stuff like that. Okay, so first one here, a plane is going west at 325 and goes into a south wind moving at 55. What is the new velocity of the plane? Okay, so we're actually trying to apply some vectors here and sort of see how this type of stuff actually works and how we can actually use it for stuff. So first things first, a really good idea is to actually sketch things out. So it says I got a plane going west. So I'm going to draw a plane. So plane, wing, there we go. All right, so there's my plane going west. And it tells me it's going west, which is to the left, at 325. And then it says there's a wind going south. So the wind would be sort of pushing it down. So if there's a wind coming along, so here's my wind, and the wind's going down at 55 kilometers an hour. Now, obviously, as the plane goes towards the left, it is going to get pushed down. So the plane's going left, the wind's going down, it's going to go down left. And we can use vectors to see exactly what the new velocity would be. So I'm just going to start with the plane. I'll use my fancy smancy arrow tool here. I'll start with my plane. My plane is, oops, where's my, there it is. My plane is going at 325 to the west. And then I've got my wind. My wind is then going to push it, and this is just the tip to tail stuff you guys are working on, is going to push it 55 south. And now we just do the exact same thing we have done before. There's no difference. I'm going to go from beginning to end and solve that triangle. Okay, so I know this was 325 and this is 55. They make a right triangle, and I can solve for the hypotenuse. So I do 325 squared plus the 55 squared, and we put them together, and we find out that the plane is going to be going around 330 kilometers per hour. Now, this is where we started from, so we want to find the angle from the resultant to the closest x-axis, which would be right in there. So once again, tan would come in handy for this. And if we solve for that little tiny angle in there, we get a little tiny, it's not going to be very big. So yeah, it's like 10 degrees or so. Okay, so 10 degrees. Now, you could wrap that angle around and say it's 180, 190. But typically, if you start with compass directions, like the west and the south, you want to end with compass directions. So you could use the 10 degrees with compass directions, and that would be 10 degrees south of west. And that would be the new velocity of the plane. It's going to be going 330 kilometers an hour, 10 degrees south of west. And if you ever been in a boat and the ocean current hits, or you're riding your bike and it gets really windy and it pushes you sideways a little bit, I mean, this is what pilots take into account all the time. Okay, all right, let's try something a little bit similar here. You got a person in a canoe is going 3.6 meters per second at 25 north of west. What are their velocities and the directions? Okay, so first thing I'm going to do is going to do a little reference here. Okay, and I got a canoe, and let's see, it says it's going 3.6 meters a second at 25 north of west. Okay, so it's going north of west. So this going straight to the left would be west, but it's going 25 north of it. So I'm going to swing that up north, something like that. So let's label a couple things here. So that's 3.6 meters per second. And there's my 25 degrees north of west. And of course, would be nice if we actually, here, draw a little canoe. Here's something like that. Okay. There you go. There's a little happy guy with his canoe. There's his oar. There we go. Okay. So we're looking for his velocities in the north and west directions, which are basically just the components of the actual vector itself. So we want to know how fast is he going west, which would be the x component. And then we also want to know how fast he is going north, which would be the y component. And we just got to break apart the triangle into x and y components. So if we find the x component, y component, we're just breaking apart a right triangle. That's all we're doing. So we do the 3.6 cos 25, and we get an x component of around 3.26 meters per second, west, or say negative, whatever, but it asks for west, so I'm just going to give west. No big deal. And then we do the 3.6 sine of 25, and we get about 1.52, so 1.52 meters per second going north. So those are the two components of his velocity. Okay, so let's try something else here. All right. A ramp goes 1.65 meters sideways and 1.4 meters up. What displacement does the ramp provide? Okay, so it says the ramp goes 1.65 meters sideways and then 1.4 meters up, and we want the displacement. Of course, displacement would be from beginning to end, something like this. So it's just a right triangle, once again. That's all this is right triangle stuff. We just got to solve for that triangle. Okay, so if we solve for the right triangle, we can use Pythagoras to find out how long that part is. And if we do that, the ramp is about 2.2 meters long. We'd also want the angle from where we started from, which is right there. So we got the 1.4 and the 1.65 with tan theta would work really nicely. And we get an angle of around 40 degrees. So if you went from down here and traveled up this ramp, you would get a displacement of 2.2 meters at 40 degrees, just like that. Okay, and that's it. Okay, notice it's the same stuff over and over and over again. Making triangles, breaking apart triangles, putting pieces together, it's all the same thing. Okay, so let's try this one here. You throw a ball at 26 meters per second at a 32 degree angle. What is the horizontal velocity? Okay, so here you are. There you are. You throw a ball. Okay, and it says you threw the ball something like this. There's the ball. There you go, something like that. And apparently you threw it at 26 meters per second at 32 degrees. We want the horizontal velocity. All right, well, the horizontal velocity would be how fast it's going sideways. So that's just the bottom of the velocity triangle. You could find the vertical part, or in this case, we're looking for the horizontal part. So we're just looking for the sideways part of the triangle down here, right down there. So that would just be 26 cos of 32, and if we do that, we can find that bottom part is around 22 meters per second, and that's it. Okay, all right, last we got a hiker goes 5 kilometers south and then 12 kilometers northeast. What is their displacement? Okay, well, I'm just draw a little reference to start with. All right, 5 kilometers south, so our little hiker guy goes 5 kilometers south, so that's straight down, and then the hiker goes 12 kilometers northeast. That's perfectly at the 45, so maybe something like that. There we go. And we'd be looking for their displacement. So that's what they started from right there. And their displacement would be from beginning to end, so from the very beginning to the very end. Okay. So here we will need to do more like we did before. We're going to break things apart, put the vectors together. So I'll make a little XY chart again. All right, so the first vector, where he started, he went 5 kilometers south. So here, let's even, here's my little hiker person, little hiker stick. All right, so they started over here, and they hiked down there. Okay, so they went 5 kilometers down. So their x component for that one is 0. They didn't go sideways at all. They just went down 5, so it'd be negative 5. And then what they did is they went hiking again, and they hiked up this way. And it's the perfect 45, because northeast is the perfect 45 degrees. So that makes things easy. And I know that is 12 kilometers long, so I'm just going to do 12 cos of the 45. And that gives me a component of 8.5. So this triangle here, that sideways part is 8.5. And I know it's 45, so my two components are going to be equal, which is perfect. So this would also be 8.5, and that's going to be 8.5. And it's going to the right, so the x is positive, the y is going up, it's also going to be positive, so we're all good to go. Okay, so all we need to do now is put the pieces together. So my total x component is 8.5, and my total y component is 3.5. So I got my components. Now let's make the new triangle. So I've got 8.5 for an x component. I've got 3.5 for a y component. And I will then use my trig and Pythagoras to solve my triangle and get my overall answer. So if I do the 3.5 squared and I add that to my 8.5 squared, I put them together, we get about 9.2. And then this is where I started from. So I want the angle from the x-axis to where the resultant is. So I want that right there. So I do the 3.5, divide that by 8.5, and I inverse tan it to get the angle. It's 22 degrees in there. Okay, so we can use that. All right, so if I look at the overall displacement, they went 9.2 kilometers at 22 degrees. I start with compass, so I typically want to end with compass. So that would be 22 degrees, but that would also be 22 degrees north of east. So if I start with compass, I usually want to end with compass. So 22 degrees north of east. Okay, so there you go. So that's applying vectors to snow, which is a little more realistic in terms of what you guys are going to be doing. It depends on the situation and stuff like that, but also sometimes you're just looking for one piece, sometimes you're looking for two pieces, and then putting things together. Okay, so there's some practice with some of all the basic vectors, components of vectors, and then analyzing vectors, breaking them apart, and putting a couple together.